In this video, we're going to learn how to build our own PIC32 circuit on a breadboard. That basically means we're going to take a raw PIC32 microcontroller in a DIP format, and we're going to build all of the minimum support circuitry that's necessary to make it work. So here's the outcome. Here's the PIC32MX170F256B 32-bit PIC32 microcontroller that comes in a DIP format, plugged into a breadboard, with an 8 megahertz crystal, a 5 volt to 3.3 volt power supply, the bypass capacitors that are necessary to filter the power, a reset button, a user button, a user LED, we've got our power indication LED, and we've got header pins to plug in the MPLAB snap to do the program. So this is a pretty big circuit. Let's take a look at the datasheet of the PIC, figure out exactly where we can see the information for how to build this, as well as just some general information about this PIC, and I'll go through the details of drawing the schematic. So anytime you're considering building a circuit, you should always start with the datasheet of the chip that you're investigating. Of course, this is a really complicated microcontroller, so here's the main datasheet for this version of the PIC. There's 350 pages to the datasheet, so that's what this class boils down to: how to read this datasheet, as well as the family reference manual, which is several thousands of pages that tell us exactly how to make this chip work. Let's start just by looking at what this datasheet gets us. The 100 and 200 series PIC32s are basically the same. The 200 series has the USB peripheral built in. So we're using the 100 series, does not have built-in USB. The 28-pin version comes in DIP format. That means it plugs into a breadboard. That's great. 36 and 44-pin versions are only surface mount, and all the other PIC32s out there are only surface mount. So a little harder to use because you can't put it in a breadboard. Where we get up to 256K flash and 64K RAM. That's a pretty good amount of memory. We get very similar peripherals as to the NU32. So if you took my class MU33 Mechatronics, you'll recognize all of this kind of stuff. But it's a MIPS 32 core. In this case, it only runs as fast as 50 megahertz. But the advantage is that the flash in this chip also runs at 50 megahertz, so we don't have to worry about a prefetch. So I guess our code runs a little faster in that way. These are fairly low power chips, but you can find more low power chips out there. They have the I2S peripheral, SPI and I2C peripherals. We'll be using all of those. This is digital communication with chips that make other kinds of signals or read signals. It's got the same ADC module that the other PIC32 we had, so it's a 1 mega sample ADC. We've got 5 general purpose timers for making timer-based interrupts and PWM. We've got UART, as well as I2C and SPI. Those are kind of like the classic communication peripherals. We've also got this thing called PPS, which lets us reorganize what pins do what functions. So not every pin can do every function, but a lot of pins can do a lot of other functions. This is kind of neat to this series of PIC. But it's also more code that we have to write to say when the PIC first turns on, what pins do what. It's got DMA to go faster. We might get there. And then as you scroll down, you just see all the different versions that they sell and the memory that it has. We'll be using the 170F256B, which is kind of like the largest amount of memory that they sell on a DIP version of the chip. So as you go through the datasheet for these kinds of chips, the first image that is really interesting is the pinout. So here's the pinout, which are the same for all of these versions. So our version obeys this pinout for the DIP. Notice that a DIP chip has a dot in the top left corner. So that's pin 1, and then it goes down to pin 14, and then 15, and wraps around 8, counterclockwise. But for some reason, and I don't know who made this sheet, pin 1 is here, and then 15 is here. So just remember that this is pin 15 down here versus, so this table over here is kind of backwards if you're wrapping yourself around the chip. So when you're using this table to figure out what pin does what, just remember that pin 15 here is not the top right pin, it's the bottom right pin, and this whole column over here is backwards. Let's look at what these pins do. MCLR, that's the reset pin. We're going to build a pull-up, a push button with a pull-up resistor on that pin. PGED and PGEC, those are the data and clock pins for the programmer, the snap. And there are a bunch of different ones that we're allowed to use on the chip in case we were trying to like reserve pins. So we'll be using PGED1 and PGEC1 for the snap programmer. The snap is also connected to the reset pin and power and ground. VDD pins, those are the power pins. That's where 3.3 volts goes. And VSS, those are the ground pins. There's also AVDD and AVSS, also power and ground pins that need to be connected. But these ones are specifically going to the analog to digital converter in the PIC. And you could do something special with these to make sure they're extra like noise proof if you really wanted, but we won't pay attention to that. There's also a pin called VCAP. The MIPS core that runs inside of this PIC actually operates at 1.8 volts. So there's an internal regulator in this chip that takes the 3.3 that we supply on VDD and makes 1.8. And we have to put a capacitor on VCAP to filter out the 1.8 volts. Then we can look at all the other pins. So for instance, OSC1 and OSC2, those are the oscillator pins. That's what our 8 megahertz crystal resonator will attach to make the chip see an 8 megahertz signal that it turns into up to 50 megahertz. The last option on all of these pins is usually how we refer to a pin. So here's A0 and A1, here's B0 and B1. This particular chip only has pins on the A and B ports, so all the pins are A's and B's. Things like SCL2 and SDA2, that's I2C channel 2. So that appears here. But if you compare this PIC to other PICs that you might have seen, there aren't many functions to all of these chips and all these pins, and that's because anything that's an RP name here, that's a reprogrammable pin. So RPB2, we'll see later, has a table that says any function of this list of functions can be on RPB2. And then in code, you get to say that, you know, RPB2 might be an output compared pin, and then RPB1 will assign that to be another function, and we could flip them if we needed to. Okay, so let's continue. We'll see the pinouts for all the other versions of this chip. That's not too interesting. Chapter 2, guidelines for setting up a 32-bit PIC. So this is what you have to pay attention to when you're building the chip from scratch. Decoupling capacitors. Anytime there's a VDD or VSS pin, or AVD and AVSS, which are the same thing, there has to be a 0.1 microfarad capacitor from power to ground. So anytime you apply 3.3 volts on VDD, you should also put a 0.1 microfarad capacitor from that pin to ground, and it should be as close as possible to that pin as it can be. You want to minimize the length of the wires. So I'll show you on my breadboard when I build it, I put the capacitor right there as soon as I attach the wire. They're also saying that these should be have a certain voltage requirement to them, and they should be low ESR. These are all properties of a capacitor when you go to buy them. They're telling you placement as close as possible. The reason for these is to reduce high frequency noise so the PIC doesn't reset itself. Okay, here's a general purpose picture of a PIC, and we see the VDD pins all going to power, all the VSS pins go to ground. We see as soon as there's a VDD and a VSS, we put a 0.1 microfarad capacitor across. VCAP gets a 10 microfarad tantalum or ceramic capacitor to ground. I actually forgot to put those in your kit, so we're going to use a 0.1 microfarad capacitor. Turns out it works okay, at least good enough. And next week we'll have some 10 microfarads to put there instead. Here's AVDD and AVSS. If you wanted to like really worry about power supply noise, you would put an inductor between the 3.3 volt going here and the regular 3.3 volts to kind of isolate them. MCLR, which is a reset, has a 10K pull-up resistor, and if you were worried about noise resetting your PIC, you would also add this capacitor and R1. We'll skip those and we'll just add a push button from MCLR to ground as a reset pin. Here's an example of the PIC32 talking to the ICSP, which is the programmer. There are a bunch of different programmers, microchip cells. We're using the snap, and we can see the pin 1 is MCLR, and I don't know why they don't arrange this in numerical order, but pin 2 goes to power, pin 3 goes to ground, pin 4 is the data line, and pin 5 is the clock line. Okay, bulk capacitors, they usually recommend having some big capacitors on the power supply. That's built onto our 3.3 volt regulator. Okay, if you're going to design a printed circuit board and you're really worried about noise, you would add these copper rings around the crystal. We're probably not going to do that because it's not absolutely necessary to work, but probably if you're going to make something a million times and you want it to work really well, you would follow these instructions. Okay, so basically you could go through this datasheet and learn everything you need to know about the PIC. What we've just covered is the minimum connections necessary to make it work. Let's draw a circuit diagram now, because before we build anything, we should always be drawing our circuit diagram. Okay, so this is my version of the PIC circuit. Of course, you could probably try to build this exactly as I did. That would be very hard. I wouldn't recommend trying to look at this picture and just copy it exactly. Really understand the diagram we're about to draw, and then build it from your diagram. So let's start with the first chip on our board, which is the micro USB breakout. Has VUSB and ground. That's a little chip. So this makes 5 volts and ground. Then we have our regulator, which has V in, V out, and ground. Okay, V in will be the 5 volts. V out is making 3.3 volts, and ground will go to ground. Then we're going to have a red LED. That's our power indicator. All LEDs get resistors in series with them, usually something like 100 or 330 ohms to limit the amount of current that goes through them. And we'll just hook that directly to 3.3 volts. So as soon as we plug in the micro USB cable to this breakout board, the 5 volts will go into the regulator, which will make 3.3 volts, and this LED should turn on. That's how we'll know we have power. If at any time where we're doing something and that red LED is not on, that means there's a short somewhere. The 5 volt line is shorted or the 3.3 volt line is shorted. That means we should unplug everything and find that short. Now, when you're building your circuit, you probably want to not have the power on. Notice that we have direct connection to the 5 volt line from our computer through this cable. So if you were to accidentally apply 6 volts from a battery to there, that would be bad. So we're going to try very hard not to apply any voltages to the 5 volt line or to the 3 volt line, which might burn out the regulator. And once the regulator burns out, then it might, who knows, pass something through to the USB cable. That would be bad. Okay, so we've already built this, I think, and tested it. We've seen that we have a steady 3.3 volt. Now the goal is to draw out the PIC circuit. And the PIC circuit has 28 pins. So if you want, you can go nuts, and it's kind of hard to figure out how to draw a circuit diagram for a chip with so many pins, but you could draw all 14 on one side and 14 on the other, or you could rearrange them and mislabel them and things like that. I'm going to try to do something like that. So pin 1 is MCLR. That's the reset pin. So we're going to have 3.3 volts to a 10K resistor. That's our pull-up. And then we'll put a push button to ground. That's our reset button. Pin 2, 3, pin 4 and pin 5. These are PGED and PGEC. These are the data and clock lines for the programmer. So I'm going to call this PGD and PGC. And somewhere we've got our snap programming device, and it has a pin 1, 2, 3, 4, 5. Pin 1 is MCLR. Pin 2 is 3.3 volts. Pin 3 is ground. Pin 4 is PGD, and pin 5 is PGC. So this PGD goes to this PGD, this PGC goes to this PGC. The snap also gets a connection to MCLR. And then the snap it doesn't provide 3.3 volts, but it looks to see that the 3.3 volts and ground are connected to be able to know that the PIC has power, so it knows it can program it. So those are the 5 connections the snap needs to have. Okay, we'll keep going down on the PIC. Over here on the PIC, there's a VSS. And then there's an OSC1 and an OSC2. Okay, all VSSs go to ground. OSC1 and OSC2 I'll call yeah, OSC1 and OSC2. We've got a 8 megahertz crystal, and it's got 3 pins. It's got an OSC1, and then it's got a ground, and then it's got OSC2. So OSC1 and OSC2 go to OSC1 and OSC2. Ground goes to ground. Okay, after OSC2, and there's some pins in here, and there's some pins in here, and there's some pins in here. We've got B4, and then A4, and then below that is a VDD. Okay, on A4, we're going to have a green LED and a 330 ohm resistor. This is our user light, so we're going to be able to blink that to know what's happening on the PIC. B4, we're going to have another push button with a pull-up resistor, so 3.3 volts, to a resistor, to a button, to ground, and that's going to be B4, and this is a 10K. That'll be our user button. When you push the button, it'll blink the green light. That's how we know that the PIC is programmed and working. And then this VDD pin here needs to go to 3.3 volts. And anywhere we apply 3.3 volts to the PIC, we need to have a capacitor, ground of 0.1 micro. Okay, is this getting messy enough for you yet? The other side of the PIC has a lot more just regular pins, but somewhere in the middle is a VSS and a VCAP. So all of VSSs go to ground, and VCAP gets a what's supposed to be a 10 microfarad, but we don't have any in our kit yet, so we're going to use 0.1 microfarad. Turns out to work just fine. And that, and the top is a VDD and a VSS. So we're going to have a capacitor go between them, and VDD is 3.3 volts, and VSS is ground. So sometimes you have to draw this twice, because that got really messy. I'd probably redraw this to make it prettier. And we kind of have sections. We've got power up at the top. We've got programming on the right. Then we've got like all the power pins, and then power pins. And we've got a reset user LED, reset user button. Okay, let's investigate how my breadboard looks compared to those things. So I've got my 5 volts coming into my regulator, going to my rails. I put wires at the bottom of my rail, so both rails have power and ground. I have my red LED and a 330 ohm resistor as my power indicator. Here's my PIC. So pin 1 is the dot in the top left. So pin 1 is MCLR, and you can see here's the reset button and a 10K resistor, and this extra long header pins, this is where my snap gets plugged in. The bottom one will be pin 1. There's a little arrow on the snap. You can see that there's a little black dot here. That indicates where pin 1 will get plugged in, so my snap will get plugged in vertically like that. Snap is also connected to power and ground, and I have 2 wires going to PGC and PGD. And then my reset button is going from MCLR to ground, so I can push that to reset my PIC. Here's a random VSS in the middle of the PIC. We've got, I already say, the AVDD, AVSS, and anytime there's a VDD, we've got a 0.1 micro. There's VCAP with a 0.1 micro to ground. This area gets a little more complicated. I've got my crystal resonator, that's the blue chip, 8 megahertz. The middle pin's going to ground. The outer pins are going to OSC1 and OSC2. Somewhere in the middle here, this red wire, that's a VDD, and I've got a 0.1 microfarad from VDD going to ground. And then on A4, I've got my green LED, and on B4, I've got my user button. Last step, plug it in, make sure we get some 3.3 volts, so my red LED is still on. Probably you shouldn't build the whole thing and test it. Probably you should build a little bit and test, and then build a little bit and test, and a little bit and test. I, of course, did that before I made the video. That way, if you build the whole thing and there's a short and you have to go back and kind of find everything, that would be annoying. Do a little bit and build, do a little bit and build. If you ever see that there's a short, then you know just in that last step, that's where the short was. Investigate around there. Okay, so that's building the PIC on a breadboard. We're going to use this for 6 or 7 weeks now. So build it as nicely as you can, nice and flush to the board, as flush as you can get it, and try to reserve at least half the breadboard for building circuits in the future. Remember, you also have a second breadboard and then the end scope and a third breadboard, so there'll be plenty of space to build things, but try to be as compact as you can. And in the next video, we're going to see how to write some code and put it on this breadboard to see if it works.